Alrighty, this is part 5 of related rates. We're going to go ahead and jump right in with an actual AP problem from 1988. This is actually kind of a classic problem as well. It has to do with someone standing in a field and observing a hot air balloon rising up into the air. It says the figure shown represents an observer at point A, so the observer's here, watching balloon B as it rises from point C. So the balloon started right here, and I'm assuming it's a hot air balloon, and then they just sort of started to light the fire, and the balloon starts to go up, and now it's at point B, okay? Of course, point B is negotiable. The balloon is rising at a constant rate of 3 meters per second. So there's our given. Our given is the fact that dy dt is equal to 3 meters per second. Now, why is that not negative? Well, because the balloon is getting higher. It's not coming down. So y is increasing, so dy dt is going to be positive. Now, when you're given a multi-part question like this, it is possible that information will change as you go from A to B to C. But usually stuff that's in the question stem won't, okay? So the only thing you really have to worry about is if the given information is in the question stem, perhaps the conditional information will be different in A or B or C. Now that doesn't happen to be the case here. All three of them say when y is equal to 50, when y is equal to 50, when y is equal to 50. So let's go ahead and deal with our conditional information based upon y being equal to 50. Well, here's the thing. This is not a Pythagorean triple, and therefore you're going to have to do a little bit of legwork, okay? And I know that when y is equal to 50, the Pythagorean relationship winds up being like this, okay? And that's basically 2 to 1 to whatever, right? Because the ratio is that from 2 to 1. So that becomes 10,000 plus 2,500 is equal to x squared, or x, when you simplify it down, is 50 root 5. Okay, so x is 50 root 5. Isn't that wonderful? So you have x and y at that conditional information, okay? Let's go ahead and go on and try and do part A. It says find the rate of change in x at the instant when y is equal to 50, okay? Well, I'm going to have to scoot this up. I hope you've written all this down. Basically, we're dealing with this, and we want how fast is the distance between your eyeball and the balloon increasing when y is equal to 50. That's what the hypotenuse represents, right? The sort of line of sight. And so we have x squared plus 100, or sorry, that's x squared is equal to 100 squared plus y squared. Sometimes, I don't know why they put x as the hypotenuse. That messes me up. So this winds up being 2x dx dt is equal to 0 plus 2y dy dt. And as per usual, the 2's cancel out when you're dealing with differentiating the Pythagorean. And you're looking for dx dt, right? And so dx dt winds up being equal to y over x times dy dt. Okay? Let me go ahead and try and fold this over so it's a little bit easier to see. Okay? Now, if I know y and x, and I do, right, when y is equal to 50, and we can go ahead and draw that on our thing. When y is equal to 50, x is equal to 50 root 5. Now, both of those numbers are conditional information, but since they're not changing from A to B to C, I'm going to go ahead and just sort of sketch them into the figure right there. And dx dt winds up being 50 meters over 50 root 5 meters, and then dy dt is 3, okay? 3 meters per second. Now, those units cancel out. Those 50s cancel out. And the only thing that's left in that ratio is that root 5 in the denominator. And if your teacher wants you to rationalize the denominator, you get that. Okay? 3 root 5 over 5. Okay? Now, what that looks like, let me go ahead and actually finally got myself a calculator. It was an investment I was hoping to avoid, but it's probably good that I have it. And that's basically 1.342 meters per second. Okay. Now, yeah, and that's about right. Because remember, root 5 is 2.2 approximately, and this is 3/5 of 2.2. So it says find the rate of change in the area of the right triangle. Okay, so now we're no longer dealing with Pythagorean. We're dealing with the fact that area is equal to 1/2 base times height. Well, in that case, the area is 1/2, the base is 100, and the height is y. Therefore, that's 50y. So dA dt is equal to 50 dy dt. And remember, that 50 came from the 100, which was meters. And so 50 times dy dt is 3. The area, of course, is going to be units squared per time, and therefore that's going to be 150 meters squared per, what was the unit of time? Per second. Okay. And that is the answer to part B. Okay. The hard part, the part that usually gets people, is part C. So let's spend just a few minutes on part C. It asks for the rate of change of theta at the instant when y is equal to 50. Well, I know that my conditional information gives me, 50 and 50 root 5. But here's the thing. I need theta. Or do I? Okay? Since you're talking about it at a specific moment in time, let's go ahead and say, well, the tangent of theta is equal to y over 100, or 100 tangent theta is equal to y. That's our equation that we're going to be dealing with, okay? So I have 100 secant squared theta d theta dt is equal to dy dt. And if you're looking for the rate of change of theta with respect to time, that's d theta dt is equal to 1/100th times cosine squared theta, because when I divide by secant squared, it's the same as multiplying by cosine squared, times dy dt. Now here's the thing. If I were to actually go in and figure out theta, it would just be a particular ratio associated. It would just be that right there. Or if I were to basically go in and talk about it, it would be theta. So, but here's the thing. As long as we're talking about that theta, and I know the sides, I don't actually have to find theta. I just have to know how to find cosine of theta. Does that make sense? And therefore, if I have 1/100th, cosine of theta is adjacent over hypotenuse, so that's 100 over 50 root 5, so it winds up being 2 over root 5 squared, and then dy dt is still 3, right? 1 over 100 times 4 over 5 times 3. Well, a lot of this reduces, and you get 3 over 125, and this is actually radians per second. Now, why is it radians? Well, first of all, if it's calculus, it's always radians, and that's going to come in handy later. But if you're wondering why it's always radians, it's because remember back when I first introduced trig to you, we talked about arc length along a circle. We talked about the area of a sector and all stuff like that. And I explained to you that theta in terms of those things is always radians, because defining an angle in terms of radians is defining it in terms of its sort of fraction of an entire revolution, rather than imposing upon it from the outside the arbitrary designation of degrees, right? Radians have more to do with the circle in and of itself and the portion of the circle that you're dealing with, as opposed to, and like, so degrees is something that's actually imposed from without, whereas radians deal with the logic of the circle in and of itself. Well, if you don't understand that, that's fine. You don't have to. Just know that when we're dealing with calculus, we're always dealing with radians. And that is your answer to part 3. Okay. Well, that was a fun one. And that's kind of how, that's oftentimes how they pop up on the AP exam. This is another one that I gave the kids a year or two ago. And it says, a lighthouse is 2 kilometers from a long, straight shoreline. Okay? So a lighthouse, and of course Pogue would love this. So we have the lighthouse. Okay, so there's the lighthouse. Like I said, never claimed to be an artist. From a straight shoreline. Okay, so that's 2 kilometers. The light makes 1 revolution every 12 seconds. So, given, okay, 1 revolution every 12 seconds. Now notice I did not call that d theta dt yet. In order for it to be d theta dt, I need to do some conversions here in just a second, okay? Now, it says, how fast is the beam moving down the shoreline when the light is 3 kilometers from the point closest to the lighthouse? This is the point closest to the lighthouse, right? So what it's asking is, if you go ahead and talk about the beam out here, okay, let's talk about this as x, okay? And this right here is my theta. It's asking, the question is, what is dx dt? Like, what is the lateral movement of the point at which the light beam hits the coast or the shoreline? How fast is it moving this way or that way? It doesn't really matter either way. When x is equal to 3. When x is equal to 3 is, of course, my conditional. X is equal to 3. Okay? So, how fast is the beam moving down the shoreline? Well, I happen to know that I can arrive at d theta dt with just a little bit of conversion. Okay? We'll call it d theta dt, but we're starting out with 1 revolution every 12 seconds, and we know that there are 2 pi radians every revolution. Okay? So we just have to convert it. And therefore revolutions cancel out, and I'm left with 2 pi over 12 radians per second, and of course that reduces to pi over 6 radians per second. So that is actually our given. Okay? This kind of goes back up here for our given information. How do I relate theta and x? I have d theta dt. I want dx dt. Well, this is opposite and adjacent, so I know that in part A, it's going to be tangent of theta is equal to x over 2, or 2 tangent theta is equal to x. Okay? So, just like last time, we're going to go ahead and differentiate with respect to t, and we're left with this. Well, thankfully, we don't really have to do anything, right? dx dt is already isolated. It's already over here. And so all I have to do is plug in for this. Now, I know that the conditional information is the fact that when x is equal to 3, okay? I don't need to find theta. I need to find secant theta. So when this is equal to 2 and this is equal to 3, what is the hypotenuse? Well, it's root 13, right? And of course, that is another piece of, that is implied conditional. Implied conditional, right? Okay, so what I need is adjacent over hypotenuse squared. So 2 over root 13 squared squared, and then d theta dt is pi over 6, and that should be dx dt. So that winds up being 8 pi over 6 times 13 is dx dt. And then, of course, that goes to 4, that goes to 3, and so dx dt is actually equal to 4 pi over 39. And, of course, this was given in kilometers per second. Now, that's kind of nasty, right? And that's one of the nastier ones. Now, part B winds up being even a little bit nastier, because this is, remember, z right here, the length of the beam. How fast is the beam lengthening if measured from the lighthouse to the point on the shore to which it is shining at the same moment? I want to know dz dt, okay? So for part B, I want dz dt. How do I define dz dt with respect to this? Well, I can do it one of two ways. I have actually just found dx dt, so I could set it up in terms of a Pythagorean. Okay, so let's actually do it that way. I know that x squared plus 2 squared is equal to z squared, and therefore 2x dx dt plus 0 is equal to 2z dz dt. And then, of course, like always, the 2's cancel out, and dz dt is equal to x over z times dx dt. I've already determined what x and z are in my conditional information, right? X and z are 3 and root 13. So I'm going to get 3 and root 13, and then dx dt is this number right here, 4 pi over 39 times 4 pi over 39, and that winds up being 12 pi over 39 root 13. Now, that of course reduces. I could have actually reduced it from up here. That winds up being 4 pi over 13 root 13. And we can go ahead and move forward from there. So that is my dz dt if I do it in terms of Pythagorean theorem. But I still have the possibility of doing it in terms of trig, right? If I want dz dt, this is adjacent, this is hypotenuse. It winds up being cosine of theta is equal to 2 over z, or secant of theta is equal to z over 2, or 2 secant theta is equal to z. Now, the only problem with doing it that way is the fact that secant becomes secant tangent, but the problem with doing it this way is z is raised to the negative 1. 6 to 1 half dozen the other. Okay, so we have 2 secant theta tangent theta. D theta dt is equal to dz dt. And of course, dz dt is equal to 2. Okay, well, let's look back at the figure. Okay, secant theta, okay, if that's theta, it's going to be adjacent over hypotenuse, 2 over root 13, 2 over root 13. Tangent is going to be opposite over adjacent, so it's going to be 3 over 2 times 3 over 2. And d theta dt is obviously pi over 6. Now, boom, 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 and that winds up being pi over root 13. Okay, I screwed up somewhere, but you get the idea, okay? The whole idea is that when we're doing, give me a second. Secant, 2 times secant, 2 secant. I probably flipped something over here at some point. Opposite over adjacent. Hypotenuse over adjacent. Oh, hypotenuse over adjacent. Hypotenuse over adjacent would be, sorry, that's the problem right there. I should have flipped that over, okay? Should have been root 13 over 2. But you get the idea. The idea is that it could have gone either way, since I already had one piece of information about the triangle. But basically, there are all sorts of things when a right triangle starts to change that are related by necessary relationships to each other, whether that necessary relationship be Pythagorean theorem or whether that be trig. So I really got to stop this. We're at 20 minutes. I'll do 2 more examples in the next one, and then that'll basically be it, and I'll go on to 310, which is linear approximation.